Back then it was called the Large Synoptic Survey Telescope. Even that got rebranded as the
Vera Rubin Observatory. Now it's Legacy Survey of Space and Time. That's the project we will undertake. We want to scan the sky as quickly as we can. Basically, we can cover the sky every 3-4 nights, and we want to do it over and over and over relentlessly for 10 years. It would take you about a year to look at every frame that we will obtain. 10 years, it's gonna be 60 petabytes of data, 60,000 terabytes.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Got with me Chuck Knight. Chuck it, baby.
Hey, what's happening, Neil?
All right.
Yeah.
Well, good. Today's your birthday.
Oh, it is.
Today.
Yes. Yeah, it was a day that will live in infamy for my parents.
Oh. And you're 29 today.
Yeah, exactly.
Forever 29.
Forever, yes.
Recently, we did a What's Up With That on the recent release from the Rubin Observatory.
Okay.
That amazing swath of data that came out.
Right.
And we said that we got to do more than just me reciting what I learned.
Oh.
Let's get people from...
Let's go straight to the source.
Let's get straight to the source.
Right to the source.
And so the person who conducted that press conference, we've got him right here. Sitting right there. You'll have to correct me 5 times with your authentically Croatian name. Željko?
Željko.
Željko.
I got to put my face in it.
Željko.
Željko Ivezic? Perfect. Welcome to StarTalk.
Thank you. Thank you for inviting Rubin team to the show.
Yes, and you flew in from UW, University of Washington, in Seattle, Washington. So thanks for coming to New York, into my office here at the Hayden Planetarium.
It's quite some office.
It actually looks like a science hoarder lives here. Right.
No, I'm just the receiver of many science gifts.
This is
That's
true.
A different thing.
It's a big difference.
Yeah. So we are talking about the LSST.
Right.
Which in its earliest incarnation, because I was on the decadal survey that sort of made sure this went into motion.
Mm-hmm.
This is now back 15 years ago. Back then it was called the Large Synoptic Survey Telescope. And even then I said, no, we can't have this.
Yeah.
And so even that got rebranded as the...
Vera Rubin Observatory.
Yes, but then you swapped
and
new
there is
words.
still LSST.
I know, but you swapped new words.
Correct. Now it's Legacy Survey of Space and Time. That's the project we will undertake during first 10 years.
That's
it's
better.
a data set.
They did better there.
That's so much better.
Yeah.
Yeah. Legacy Survey of Space and Time.
That's badass.
Yeah, that's badass. That sounds like it could be like part of a movie. You know what I mean? There
is a tiny problem with that, though. It's very hard to translate it to some languages like Spanish or Croatian, where you talk about legacy, people think you died and left something behind. In English, it's perfect. Yeah,
okay. Very important there. And named after Vera Rubin, who was an astrophysicist. I knew her, and she visited Princeton often when I was there. And I think we first met at Princeton during your...
Thanks to Robert Lapton and Michael Strauss.
Yeah, two key components of the astrophysics landscape in the Princeton campus.
The Princeton campus?
Yes. And so she was a big observer and of galaxies and try to figure out what stars were doing within them, discovering dark matter. She and her colleagues, Kent Ford, one of her collaborators.
They did great measurements that were very simple to interpret and very convincing that there is something fishy with gravity.
So with this telescope and your role in this, what I have you down here, you're the director of the construction project. Oh my gosh.
I still am. A few more months.
I still am.
Okay. So it's still getting refined and built and tested.
By and large, we are done, but now we are fine-tuning the system. It's a very complex system, especially the software.
Right.
So we are learning how to optimize it. And then in a few months, in October probably, we'll be done with construction, and then we turn it on. And it's effectively a robotic telescope, robotic observatory. We are not going to think every evening, like, let me look at this, let me look at that.
That's the old days.
It would have
That's
to be.
the old way.
In the old days, yeah. It's so what I think people need to appreciate, if they don't already, is that modern observations are more about the the data pipeline that comes from the detector more than it is just what you're going to do with the telescope.
Right.
Right? I mean,
Exactly.
and so can anyone apply for time on this telescope, or does this telescope already have an agenda that it's going to
We
accomplish?
have a very strong agenda, and it's very simple. We want to scan the sky as quickly as we can. Basically, we can cover the sky every 3-4 nights, and we want to do it over and over and over relentlessly for 10 years,
Every single night.
Every single night.
if it's clear.
So it's like, my father was a printer, and in the dark room, that's the time is the development. So is that kind of the because you say it's the same sky over and over and over. I can only assume that you're layering image over image over image to get more and more light that gives you better, deeper.
Oh, no. It can do that, but that's not the point.
Oh, get out!
It's one of the 2 points. No, Chuck is right. You add many images together and you see more and more objects.
Okay.
You
But
can see
Neil is
deeper,
right too.
deeper and
And
deeper.
Neil is right too.
Yeah.
Because we want to look what changed between these different.
Well,
So there are
that
two
is even
things.
more key.
That's right.
I got you.
Because any ordinary telescope can just stack images,
Right.
And what you're really doing when you're stacking images, there's a noise level in the background,
Right.
a visual noise,
Right.
And every next image you stack, it tamps down the noise.
Okay.
But if there's a signal there, the signal gets boosted.
Nice,
Right? It's nice. So the noise drops, the signal goes up, and the signal to noise ratio,
Right.
as we say, goes up. And so you're going to get that regardless. But the real contribution to this landscape of data is you're making a movie of the night sky.
That's amazing. You guys are like the early days of Walt Disney, but for observatories.
It's a much bigger movie. We call it the greatest movie because it would take you about a year to look at every frame that we will obtain.
Wow, you guys actually beat out Jesus for the greatest story ever told.
All right, I'm leaving. You guys are funny. You know astronomy. I can leave.
Protect Chuck from himself here.
Exactly.
Right. What fraction of the nights do you expect to be completely clear?
About 300 nights per year. So that's
too
like
bad.
80%. Yeah.
Wow.
Not too bad. And of course, the sky shifts a little bit each night. And so in December, you're not getting the same sky you're getting in June.
Correct.
How long is your movie that you will have?
So the movie will be 10 years long.
Okay.
Now, some
Man,
parts of the
that's
sky
a director's
you
cut if
always
I ever heard one. That is a serious director's cut.
Directors, they don't leave nothing on the floor.
Exactly.
They put
10
everything.
years.
10 years. It's going to be 60 petabytes of data, 60,000 terabytes.
Yeah.
It's mind-boggling.
That's
Okay, but I
crazy.
guess what I want to understand is for any given spot on the sky, you have continual coverage, not for 10 years. You have it for 6 months.
Well, some parts.
Yeah. Oh,
Some
of
parts
course.
close to the pole, you see
You see continuous.
always. And some parts that are closer to the equator, we will have like 5 months, 6 months, 7 months. It depends.
That's
where
the point I was
exactly
making.
you are. Yeah.
Right. So if you're near the pole,
Right.
we call those circumpolar stars.
Right.
They never rise and they never set.
Right.
Because the pole star is above the horizon.
Right.
And the stars just go
Just going
around.
around it.
Yeah.
Yeah, that's
and
brilliant.
so throughout the night, you get it the whole time.
Right.
Yeah.
So in 10 years, we'll see each object about 1,000 times. And for some objects, it will be uniformly distributed over 10 years. For some, there will be clumps of like 6 months, and then few months, no observations, and then again, few months of observations.
But suppose something happens when you're not looking.
Tough. Tough luck.
I like it.
That's the way the cookie crumbles.
That's the right attitude.
That's right.
No, it's very frank.
But we'll also catch a lot of them.
Right.
Right. So what are the high points of expectation? Well, let me say that differently. For objects very far away, galaxies, if a star goes bump in the night, you'll see it. If we have a supernova or a nova, all right?
Mm-hmm.
But those are too far away for you to see anything moving. So there you're checking for changes in the brightness of an
Yep.
object,
Mhm.
whereas much nearby, you're looking for movement of objects,
Exactly.
such as asteroids.
Asteroids or stars in our Milky Way, they move too, but much slower than asteroids. So you really need to wait for 10 years to reliably see that motion of stars that go around the center of our galaxy. We are going with them.
Yeah.
And so we can see relative motion. With asteroids, you look at it and within half an hour, you are definitely certain that there is motion.
It seems to me your biggest contribution to the astronomical data sets that we currently have will be in the discovery and tracking of asteroids.
That's one of the 4 pillars that we have. So it's studying the solar system, asteroids. Then the other one is studying the Milky Way, stars in the Milky Way, about close to 20 billion stars, more than living people on Earth. Then we want to study cosmology. We want to look at galaxies and supernovae to try to decipher why do we see accelerated expansion of the universe. There are basically 2 ways to explain it today. One is to postulate Einstein's theory of gravity is correct, which leads you to conclusion that there is some mysterious fluid called dark energy, of which we know nothing. The other possibility is that Einstein was wrong, and theory of gravity is wrong, and we need to fix it. And people already proposed many different ways to fix it, but we don't know which one of these 2 is more correct or less wrong. And we don't know it now because we don't have data.
I'm betting on Einstein here.
It's not a bad bet.
If I'm just coming in blind.
I'm going to say the Vegas odds are like, 6-5 on Einstein, but yeah. So let me just get a layman's perspective here. When you talk about dark energy, that is the pressure that is speeding up the expansion of the universe. What are you looking for that demonstrates that?
There are several ways to do it. So supernovae, of course, play a major role. They directly measure the expansion. They tell us acceleration. But then to get handle on gravity, you have to look at the effects of gravity.
Okay.
One of them is the formation of structure in the universe. When you look at galaxies on the sky, they are not randomly distributed. Like take a handful of sand or salt, throw on your table. There is not much structure. But when you look at galaxies on the sky, they have these clumps, and then there are voids where there are no galaxies. We want to measure this very precisely. That's one way to do it. The other way is so-called gravitational lensing. That goes back to Einstein, where light is curved because of mass. And so by looking at that curvature, which distorts images of galaxies, we can tell how much hidden mass there is. And so all these together...
So your dark matter will also curve the light, even if you can't see the matter at all.
So you need many different probes to decouple these different influences. And so we know that in order to make the next scientific step, we need to measure about 10 billion galaxies. And you just can't do it with existing observatories. You could, but it would take 1,000 years. 1,000 years.
Right.
We'll do it in 10 years with this new observatory.
So you're able to do that because you have like a wider field of view? Or?
Yeah.
Correct.
You think?
Go ahead.
How much bigger is your field of view in one snapshot? Can you say that? How much bigger your field of view than that of the Hubble telescope?
Oh, interesting.
It's about 1,000 times bigger.
Oh my God.
So typical telescope sees a part of the sky that is much smaller than full moon.
Right.
And in our field of view, you could fit 45 times the full moon.
Oh, wow.
It's much larger.
Gotcha.
So if Hubble were to do this, they would have to sit there and take one picture here and one there, and then mosaic it all together and get the big picture.
Right.
And by the time that's had, we're all dead by then.
Yeah. So this is like the introduction of panoramic view on the camera phones when it first came out.
Exactly.
Everything was like, they were like, oh man, you don't have to take a picture here.
I like analogy with tiles in your bathroom. If
Tiles
you
in
want
the
to put
bathroom?
new tiles,
Right.
you could use Roman mosaic, those inch by inch. It would take you a whole weekend to do it.
Right.
But if you go Home Depot, you get these good American big tiles. You go slap, 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 and you're done in half an hour.
That's a great analogy.
To get on to your next
I love it.
Right.
That's funny.
So, but I still like to think that what it's doing compared to previous images is way more than just your panorama setting on your iPhone.
On the iPhone?
Just
a little bit. Just a little bit. Just a little bit more than that.
Instead of taking 5 pictures, I take one. We're talking thousands,
Right.
And so this, of course, you have this huge camera and detector
It's a big, beautiful camera.
big,
Big, beautiful camera.
3,000 megapixels.
That's it. 3,000. It's the biggest camera. And what we're trying to figure out is how it can take a picture of me. Get ready to leave the world behind because on Paramount Plus, Star Trek Strange New Worlds is back for an all-new season of genre-bending adventures, romance, mystery, action, space zombies, special guests. This show is going where no show has gone before. One show, infinite adventures. Don't miss the new season of Star Trek Strange New Worlds, premiering July 17th with new episodes on Thursdays only on Paramount Plus.
So it seems to me that some of the public will be very much interested in dark matter, dark energy, because it's a big mystery, and we all love mysteries. Other parts of the public might want to know more about those asteroids, because we've all seen asteroid movies where an asteroid comes our way, and Bruce Willis, and the odd thing is, holding aside that the movie Armageddon violated more laws of physics per minute than any other movie ever made, the scenario that an asteroid could be headed towards Earth is one that has precedent on Earth.
Right. Yeah.
Okay?
That's a movie that actually would be a rerun.
Okay.
It's already happened.
That's already happened. So, in terms of, I don't want to say national security, global security. You will have better data than any Air Force, Navy, Army data could possibly accumulate on the risk factors of Earth getting hit by an asteroid. So, do you have a relationship with the military on this?
Or Bruce Willis?
We don't. So, if we had relationship, it would be with NASA, with their Planetary Defense Office.
Right.
But because the nature of our data is to look at everything on the sky, these potentially hazardous asteroids will be like gravy on top of everything. We don't have to do anything special to find them.
Oh, they come in for free.
And because the system is so powerful, we will indeed be the most powerful machine for finding new asteroids in general and potentially hazardous asteroids in particular.
What he's saying, the men in black haven't shown up yet.
Exactly. Yeah.
They're going to show up.
That's funny.
I caught you on that press conference just a few weeks ago. And brilliantly executed and very exciting.
I was just pizza delivery guy. At the end of a great supply chain, we had fantastic team that produced all those great images and videos.
And they had their day in the sun there, or day in the media, which is good and important, of course, because you work most of your life.
It was an awesome day after 20 years of working hard on this.
Yes.
To see thousands of newspapers and thousands of TV stations pick up our images.
And that's an authentic interest. They were not bribed to attend your press conference.
Exactly.
So what intrigued me most about all the data, because I've seen pretty pictures of nebulae before, and you zoom in better than anybody else. Okay. But excuse me, after, was it 10 hours, there's thousands of previously undocumented asteroids showing up in your data? Thousands of them?
Thousands.
We discovered more than 2,000 in just a few nights.
Wow. Wait. In a few nights of 2,000.
You identified all these asteroids, none of which are in any catalog.
Wow.
Correct.
That's out of control.
There are about 1 million known asteroids now. And in first few years with LSST, we'll discover 5 million more. So we'll increase the number of asteroids by factor of 5 compared to last 200 years of people discovering asteroids.
Right.
Wow.
That's technology. That's rapid development of technology.
It's not because we're smarter. It's because...
We'd love to say we are so much smarter than our forefathers, but it's because of technology.
Yeah. Yeah, the first asteroid, you know when the first asteroid was discovered?
No.
1801, I think it was.
Wow, that's soon.
That recently?
That recently?
Yes. Well, after Galileo and Newton and...
Oh, yeah. All those guys looking up before then, you would have thought.
Had no idea.
No idea.
Right.
Ah, look at that.
Yeah. So is there people tasked specially for the asteroids?
We do have a group that keeps an eye on it, but it's all done by software.
Right. Got it, of
so
course.
It's automated.
Okay. So what role does AI play in this?
To assess whether what we discover actually makes sense. So it's all done automatically. AI comes in many places in our observatory, from running the observatory to decide where on the sky you're going to look at, to interpretation of images, classification of objects and such.
Probably one of the best things AI does, period, is pattern recognition. So I would assume that all these changes that you're looking for, that's going to be a big part of what the AI does.
Absolutely. There will be so many objects, as I said, billions, more than living people on Earth. Mm-hmm. So you really need then to be able to notice one tiny change among billions of them. And that's where AI comes in. We couldn't do that without AI.
Okay, so it's noticing a change. Now, do you anticipate discovering a kind of object that has no known precedent?
every project prior to us, every project that was breaking technological barriers, that was at the cutting edge, every project discovered something they did not expect.
In the history of
In
science.
history of astronomy and science in
Yes,
general. Right?
yes.
So we think we will discover something super exciting, but I can't tell you what. We call it unknown. But our power to look at the sky, to see what's changing on the sky, power to measure things more precisely than anything else before, that is what gives us confidence we'll find something super cool.
So more precisely, you're referring to the resolution of the...
It's
the
resolution,
image.
it's sensitivity, the amount of data, relentless scanning of the night after every few nights, of the sky after every few nights. That's what gives us confidence.
Now, I don't mean to value judge what you're putting together there, but for me, the least interesting objects would be the variable stars. Because we've had variable stars.
Tell me again what a variable star is.
It varies in its brightness.
Gotcha.
Yeah, that's how we roll in astrophysics.
Yeah, you just, what it is, you give it where I am is what you call me.
Well, there is American Association of Variable Star Observers
AVSO,
who don't like
yes.
you right now. They don't like you right now.
Okay, it'll feed them their breakfast, lunch, and dinner like forever now. It's just that most stars vary at some level. You're going to find variations that...
Even the sun varies.
Yes, exactly. So at some level, every star is variable. And so if every star is variable,
then no star is actually variable.
then variability is not a designation.
It's not a big deal.
If we all vary,
Right.
then
It's like if
then
everybody's
who's special?
If everybody's special,
Then nobody's
special.
So what kind of stars would be especially interesting in the variable star category?
I think interesting events are when there is some microlensing with planets. Then we can see that star has a planet. So we'll get some of those. But we'll have hundreds of millions of variable stars because we'll have 20 billion stars overall. So it's like totally new ballgame. We are changing it from millions to hundreds of millions. It's like someone increased your salary by a factor of 100. Would you live differently?
Yeah,
Probably.
I would probably live differently. Yeah.
So is there any, because you brought up Hubble just a little while ago. So when we look at the detail that Hubble came out with, are there any areas that you might find where you'll just put it over to them? Like, hey, you should look at this. Or does that not make a difference?
Are there telescopes that would be interested in follow-up measurements?
Yeah, absolutely.
With whatever is their specialty, which could be different from your telescope's specialty?
Absolutely. That's
Either
one of
in
the
wavelength
goals.
or this, because Chuck was trying to inquire about that. Yeah.
Fun fact. When we get a new image in Chile with this observatory, it's shipped to California for processing within few seconds. Within 60 seconds, that image will be compared by computers to all the previous images we obtained from that part of the sky. Everything that is new in that image, it changed in motion, it changed in brightness. We will report to everyone in the world who is interested within 60 seconds. And every single telescope in the world, should they wish so, can go and do follow-up.
Yo, that is gangster. That's
in my day,
my day, we had to actually look through a piece of glass. We actually had to be nighttime. And
No, in my day, if someone discovers something, we're very organized, my people. Mm-hmm. We got each other's back. If someone discovers something at a telescope, back in the day, they'd send out a telegram. And there is this special telegram service just for us.
Just for you guys?
Okay? And it would show up in the observer. And before you went observing that night, you check to see, is there a star that just blew up? Is there something that just moved? Is something? And if it can fit into your program, you would get you would part your own observing program to get data on that object. And then you send it back to them.
Wow. That's...
And you're observing the object, you're monitoring the object, but then the sun rises. For you.
Not for the guy over there.
Not for like 6 hours over in time zone, and they can pick up the observation.
Hand it off, all through telegrams.
So you should be able to do that, right?
Absolutely. So Hawaii is the first place with telescopes that comes on after Chile. Then you go to Asia, then you go Europe, Africa, you come back to Chile. So we have... The sun never sets in Rubin universe.
Oh!
That's very cool. That's very cool. Now, do you guys also use Telegram?
But he did use the word ship. He said it ships to California.
Right.
Ship. I'm thinking of, Spanish galleons, but
Yeah.
no.
Good evening, Mr. and Mrs. America, and all the astrophysicists who see. Dateline, we have a new image. Okay,
We
sorry.
now have fiber optical cables going from South America to US,
Oh, wow.
two redundant cables. But when SDSS, previous big astronomical survey,
The Sloan
started,
Digital Sky Survey.
I remember going with a doof bag full of DLT tapes from New Mexico to Princeton carrying this data.
Duffel bag.
Duffel bag, what did I say?
You said doof bag.
Oh, duffel bag, duffel bag.
Doof bag could be heard differently.
A dupe bag is a
cut it
bag
out.
full of stupid people.
Cut it out, cut it out.
A bag full of doofs.
Yeah.
Doofs.
A bag.
So it would be physically carried.
Correct.
Yeah, I
That's-
remember we would compare back when bandwidth was narrow,
Right.
and speeds were low baud rate. We had to calculate: do I send this through over the computer? This is early '90s, late '80s, or do I put it on a disk and send it by FedEx?
Right.
Okay, so there's the bandwidth of FedEx.
Wow. And now it travels at the speed of light.
Close.
Close.
Well, yeah, it's fiber optic.
Yeah,
I mean, Verizon says it's the speed of light.
Well, you have to divide by the index of refraction of the glass.
That's right. I understand because it slows down light.
Exactly.
It's a medium that slows down light itself.
Yeah,
I got you.
yeah, all
I
these-
remember
Super
that.
fast.
We did
I
a thing
remember
on that.
one. Yeah,
I think we did a
we
little-
did a whole thing on
the
it.
thing on
all
that.
the different mediums through which light actually slows down.
But technically, light always goes at the speed of light.
Right.
Because it's light.
It's light. Exactly. You know how fast you were going there, sir?
I'm light. So
Yeah, I
I'm-
was going me.
So the photon checks into a hotel,
Okay.
and the bellhop says, "Do you have any luggage?" The photon says, "No, I'm traveling light." we have queries for this episode.
Oh, I forgot. This was so good. I forgot we
I
actually
didn't
have
forget.
people. Yes.
I didn't forget.
Yeah.
These are cosmic
I
queries
should
for
get
the
those-
Rubin
I should
telescope.
get them ready.
With the man himself.
I should get them ready.
Yeah. So we have a fan base, and a subset of the fan base actually pays monthly to participate in ways. They have little extra benefits. One of them is they get to ask questions at the entry level. You got questions here?
I do. I have
Let's
them
do
ready
it.
to go.
So
Here we
give
go.
me a few.
All right. Let's start off with Hugo Dart, who says, "Hello, Doctors Tyson and Ivezic and Lord Nice. This is Hugo Dart from Rio de Janeiro, Brazil, with my 7-year-old daughter, Olivia, who is a big fan of StarTalk."
That means she's asking all the questions here, not him.
Right. Here is
Grown-ups try to sound so smart,
Right.
but it's their kids
the
who
kids who
pumping
actually
it.
know the deal.
Yeah.
Right. Here is our question. Public access and open data are key principles of the Rubin Observatory.
Good.
How do you envision citizen scientists, educators, and students using this data, and what tools are being given to develop and support them?
We all heard or read that all the data will be made available to people essentially instantly. So everyone can participate in this. So what are the plans for that? And I like that. What tools? Because you can't just say, here's the data. They have to know how to get into the data. Is there a tandem set of tools to support the citizen?
Now, Rubin Observatory and LSST are not just for scientists, they are for everyone. And we have a large suite of tools that you can use to get to our data. A couple of weeks ago, you could see that thing called Sky Viewer that allows you to zoom in, zoom out, enjoy the night sky. But we'll have many other tools on top of that. And Hugo is asking
Wait
about
a minute,
citizen
sir.
science.
You're telling me people will no longer have to look up because they can see the sky looking down on their iPad because you brought the sky down here. Now no one's going to look up because of you.
Yeah, but you can't see what you can see down there, up there. With
You can always look up.
Yeah, exactly.
You can take a laptop or an iPad. You look up, right?
That's great.
You got me there. Okay. So you have a suite of tools, and where do we find those tools?
You go to rubinobservatory.org, and all the links there. Actually, there is already ongoing citizen science project with comets. My colleague Colin Orion Chandler from University of Washington just started a few days ago. They already have hundreds of thousands of images processed by human eyes. I forget how many thousands of people in the first week of that project are already enjoying Rubin data.
So these are people looking for comets.
They are looking at things that move, and the question is, does it look wider than star? Do you see any evidence that it's a comet and not an asteroid?
With fuzz.
with fuzz.
Right,
Is
right.
it
Because an
fuzzy ball?
asteroid is just a dot of light on your frame, and stars are dots of light on those same photos.
Right.
So when Herschel saw them, he said, "This kind of looks like a star, but it's not,
Right.
because it's really nearby and it's moving. So it's star-like." Asteroid.
Nice.
Asteroid. That's where we get that name.
Yes.
But if you have AI finding everything, how can a human being actually participate in this?
With AI, you need training sample.
Mm-hmm.
And so training sample has to be as similar as possible to what you're actually doing. And we are just starting now our project. So now we are getting people to help us make a training sample. And then we will use training sample to train AI that will do it automatically.
Interesting.
So these people are helping a lot to deploy AI later.
And he talked about looking for fuzz, so you can
Right.
find the comet. The inverse of that happened. Fascinating research paper by William Herschel.
William Herschel.
Okay, he's looking at the night sky,
Mm-hmm.
and he sees an object move. Okay,
Right.
and he said, "Must be a comet." This is before asteroids were discovered.
Right.
It must be a comet. He keeps watching it, and there's no fuzz
Right.
on the comet. And he says, "This is an odd comet." And he published a paper, an account of a peculiar comet. And he said that it refuses to show fuzz.
Right.
The man discovered planet Uranus.
Wow.
That he discovered. That's
right.
but he was in denial because no one had discovered a planet before.
Right.
So why would he think he's discovering a planet when everyone has discovered comets before? We had comets forever. Okay, so that's a funny inverse problem here, where there was no fuzz, therefore it was a planet. Are you going to be able to find Planet 9 if it's out there? Do you think?
If anyone will find it, it will be Rubin Observatory.
See,
Right.
Nine's getting cocky.
No.
If it exists, and if it's in the right part of the sky, and if it's large enough, we have the best chance of discovering it.
Right.
But
See,
there is no
that's-
guarantee we will.
That's badass.
That is pretty cool.
That's
man.
like,
Yeah.
if it's out there,
If it's out there,
no one else will get it before we will.
the answers are out there, Scully.
There were many previous projects that looked hard.
Right.
And so they said that their sensitivity level, they didn't find anything. And now we are pushing the sensitivity. So I'm not being cocky, I'm just stating the fact.
It's not cocky when you're right.
Exactly.
Yeah, I'm not being cocky. If we all know that I can kick your ass,
Right.
that's just the
That's-
facts of the
that's so
situation.
great.
So, remind me, what is the latitude of this observatory?
Minus 30.
Minus 30. So you can go circumpolar to the South Pole, but you'll be missing a cap in the sky in the north.
We will.
And what fraction of the total sky will you never be able to observe?
Never ever about 1/4, but our highest quality map of the sky and movie of the sky will be for half the sky.
Half the sky. Okay. So this calls for a twin of your observatory in the north.
There you go.
It would be hard to justify it in scientific terms because we'll get most of science done with just half the sky because of statistical effects and so on. But it would be fantastic to have another one in the north, I agree.
Unless the asteroid is coming from the north, then he's gonna miss that one.
Yeah. I mean,
I'd like to have 8, like 4 north, 4 south, and then at different
Yeah,
longitudes.
then it's continual.
Exactly.
Right.
exactly.
wow, that would
Then no killer asteroid could escape. We catch them all.
Catch them all.
Unless they're peculiar comes from the direction of the sun, but there is medicine for that too.
Plus, as we move around the sun, you can't always stay behind the sun unless it's being intentionally hidden there.
well, that's aliens at that point.
There are some interesting asteroids that go around the sun in orbits similar to Earth's orbit. Takes almost a year for them, about a year to go around, but they're on the other side of the sun. So for us to see them, they're basically hiding behind the sun. So sometimes takes 20, 30 years for them to move enough for us to detect them.
And we just learned, and we did a little explainer on it, how Venus can hide asteroids in 2 Lagrange points
Right.
that orbit with Venus. But Venus is always near the sun. Venus is never the opposite direction because it's interior to us.
Right.
So if it's got asteroids that are hidden there, we will never see them because they're lost in the sun's glare.
Right.
And if they get like nudged, they pop out of their orbit, they're a risk factor. Yeah.
Yeah.
I don't want any asteroid coming to us without your warning first.
Will do, sir.
Yeah.
This is my finger.
Not that it will make much of a difference. We can't even pay for a warning system for floods.
I know. Just
So
I'm not going there.
I know, right, right.
this is James Liggett, and he says, "Hi, y'all. This is Jim Liggett from Midland, Texas.
Midland, Odessa.
The-
That's a twin city there.
What wavelengths of light does the telescope see, and what is the reason for that choice?"
Good question. Let's start with just human vision. Can you see all the wavelengths that the human eye can see?
Yes, we can. So let's from 0.4 to 0.7 microns, we see everything
Wavelength, yeah.
that
Okay.
eyes can see, but we see more, a little bit more.
Okay, so now you got that. So now keep going.
Now you go towards shorter wavelengths, towards ultraviolet, and there we
Just
go.
on the other side of violet.
So
ultraviolet.
it's cut off by the atmosphere. And so we see everything you can if you're on the ground. And then on the other side, towards near infrared, we go all the way to the sensitivity of silicon, roughly 1.1 micron.
The CCD chip,
Right.
its sensitivity drops off after a certain wavelength, but you got it right up to that edge.
Exactly.
Okay.
So we are doing as well as we can from the ground, unless we use different detectors. If you want to go into shorter wavelengths than UV, you have to launch telescope above the atmosphere.
Right.
So why don't we put Vera Rubin telescope
In
In
space?
space.
There are two basic reasons. Our data throughput is so large that we couldn't downlink so
Can't
much
transmit
data.
it.
And it would be very, very expensive.
Right.
Right.
Well, so I mean, I said that almost jokingly, but one can imagine a future where you would build Rubin telescope on the moon.
You could.
Oh,
right.
that makes
and
sense.
then it's still sort
Right.
of it's got a ground
Right. It's got a ground base.
structure.
And, yeah. Yeah.
It's certainly technologically possible.
Right.
It's all about funding for it and justification.
Oh, is that what it's only about? Funding? Is that all?
Well, there you have it.
Yep.
It'll never happen.
So, what other telescope in the world at another country comes close to Rubin?
The closest one, so you need to have large telescope, large
Large
field of view, and camera to support it. So
Yeah.
the one that is the closest is Japanese Subaru telescope
Okay.
with hyper supreme camera on it, and the telescope is sited in Hawaii.
Okay, and that telescope's been around a few decades, if I remember correctly.
Right. So they refurbished with a new camera.
Right.
And so if they spend all their time using that camera to scan the sky, so they would be about at 1/10 of our speed. We are about 10 times faster
Okay.
than them, but they are not using all the time for that
Of course.
program. So we are close to 100 times faster than our competition.
Okay, so one can say that the United States leads the world right now in
Correct.
this way. And so going in the future, it's a matter of, do we want to keep leading the world? Because we have a lot of innovative ideas that are on the docket. You know, this is not the only great idea telescope anybody's ever had, right?
Right.
And so it'd be interesting to see going forward how we value our leadership in these areas in the United States. So, and allow me to say that from beginning in the 20th century, the United States has prioritized leading the world in astrophysical observations of the universe. We've had biggest telescopes like forever, right?
Correct?
Yeah. And so you make the biggest telescope, you get all the data, and then you say, okay, now we have a technology that can make an even bigger telescope, and bigger is better. It's just how
Well, it makes sense.
that's how, because you can get more light, more data. That's how that goes.
Maybe that's the way we can get funding. Just keep telling people that it's the biggest.
I do believe that today we need more coordination between different nations around the globe because these instruments are becoming more and more expensive.
Right.
So the plain competition where you make two of the same thing and try to compete them, that makes no sense.
Makes no
Right.
sense. In modern
so
times.
why not allow people to concentrate on different areas, different technological advances, and then share the information?
Exactly.
Yeah, and then
Well,
you
everybody
get,
does what they do best, and you make the one
and you
amalgam
make
from
yeah,
it.
yeah, right.
Yeah.
Yeah, that makes sense.
And our project shows nicely where United States is very strong. That's software, that's new algorithms, that's this new technology.
And AI, yeah.
The reason why Google and Facebook and Amazon is in the States is this huge base of people who are great at software.
right.
Yeah.
Historically and today. And our project was enabled by this great expertise in software domain, in computer science in United States. And that's what we don't want to fall behind.
Absolutely.
But I have a book here called Cosmic Discovery, written by Martin Harwitt.
Okay.
It came out 45 years ago, but he made the point, as a follow-on to that a few years later, he made the point that we can dream up whatever we want in the universe, but at the end of the day, the technology that enables it is what creates the leaps and bounds in our discoveries.
Absolutely.
Right up and down the stack. So,
go
for it. Give me another one.
You just gave the next question.
Okay.
This is Yogesh Jog, who says, hey, quick question. We use telescopes to observe the universe, but are they enough? What else do we need to truly monitor the cosmos? And have we even identified everything required to do that? So are telescopes the only game in town? Is that all we really have if we want to look out into the universe? Or are there other things that we might be able to utilize to augment or add to that?
As Neil already pointed out, we don't see the whole sky.
Right.
And we see it only during night, not during the day. So it would be great to have at least 2, maybe 8 similar observatories. Then there are different wavelengths. And so you want to get some instruments above the ground. That's, for example, another fantastic US project, Grace Roman
yes.
telescope, which will be fantastic. Also, huge field of view above the atmosphere, sensitive to different wavelengths, longer infrared wavelengths that will give you different kind of information about the universe than we can get from the ground with Rubin. So together, these two will be a great complementary missions.
And kind of today, we're no longer limited to thinking only about electromagnetic energy, light, because we have the gravitational wave observatory. How about we have neutrino?
Both of these, we are going to try to get electromagnetic counterparts if they trigger us. We do have, you asked earlier, are we always going to just do the same thing over and over? It's true at the 98% level, but we reserve about 2% of observing time to interrupt what we are doing if there is a great trigger coming from LIGO or from IceCube Observatory.
IceCube is the neutrino observatory embedded in Antarctica. Yeah.
Right.
So a few times a year, they'll tell us, something interesting happened, new gravitational wave source, go and find what is the counterpart.
And you could easily donate or forfeit, you can easily allocate a short amount of time to get some good data.
Correct.
And then you go back to your continued movie.
Mm-hmm.
Yeah.
Cool.
Again, that's more we got each other's back on this.
Yeah.
Very good.
No, the only people more collaborative than scientists are rappers. So,
can you do on my album? I got an album coming out.
Yeah.
So just let me emphasize what you just said so casually. We make an observation in any one of these domains so gravitational waves, neutrinos, and who else knows what else might come down the pipe. These would be coming from extraordinary phenomena in the universe, colliding pulsars, whatever, and not all of the data arrive at Earth at exactly the same moment. So what gets here first? Is it the gravitational waves that's moving at the speed of light?
Right, neutrinos.
And then neutrinos come a little later.
A little bit later.
Just a little bit later.
Teeny tiny. Then electromagnetic part, photons, they could come much later because some time is needed for this energy to get through the local environment to produce the emission that we would see.
Okay, so you can just watch that happen, and now everybody's got a piece of the action, and you bring it together, and we can then describe this animal that is an elephant that would otherwise be unthinkable.
And the electromagnetic part lasts longer, so even if you don't catch it at the beginning, you can still get very useful data that will inform you about what's going on.
Right, so it's not just a fuzzy tail and toenails and tusks and a trunk. Somebody can know that we're looking at an elephant.
That's wild.
Nope, that's lame. Ready? Do you harbor questions about the universe? Some long-held bit of cosmic curiosity lingering within you? Or questions about anything at all? You can become a Patreon supporter of StarTalk. You have access to our exclusive question line on our website. Those are where we draw our questions for our cosmic queries.
Some of the most extreme objects in the universe.
StarTalk is a work in progress where we, every month, come up with some new way, some new idea, some new understanding of how to bring the universe down to Earth. We could not do that without your support. Thank you. And as always, keep looking up.
This is Holly Sweet. That's a great name.
That's
by
a
the
great
way.
name. Okay,
Yeah.
that's good. Uh-huh.
Hello, Dr. Tyson, Dr. Ivezic, and Lord Nice. I was wondering, during the building process, when the telescope is installed and the observatory is up and running, how do you keep everything clean and pristine to prevent foreign objects from interfering with your research? Thank you, Holly Sweet from Mount Holly, North Carolina.
All right.
All right.
So it took some effort. It's a great question. It took some effort to clean the observatory after construction.
Right.
So we
That's
don't
true for
want-
any construction site. There's construction dust and the like.
But
Yeah.
here it's especially sensitive. And what we care about the most is our mirror, which is very sensitive. And indeed, even though we are trying to protect the dome where the mirror is, every few years we will need to coat the mirror with a thin layer of silver to make it shiny again. It loses its shininess.
Right.
Is it a solid mirror or segments?
It's a solid mirror. It's
Solid mirror. And what's the diameter?
8.4 meters is the outer diameter. It's actually two mirrors in one. It's like one disc that has two optical figures. The outer one is the primary mirror. And then inside, the inner 5.4 meters is a different optical figure that acts as tertiary mirror.
Oh my gosh.
It's a very
That's
unique
brilliant.
optical design that allows us to have very large field of view without very strong distortions.
Right.
Wow. So, Holly, the answer is ShamWow. That's what they use to clean things.
Chamois. Chamois cloth. Is there a spider mount for a secondary?
Correct. There is.
Okay, so you will get diffraction spikes.
We will.
Okay.
4 of them. Yeah.
Because you know all the pictures that show the spikes?
Right.
That because it's an
Yeah.
artifact of the detector,
Right.
of the system.
Yeah, it's not the actual star going,
No, that's right.
right? yeah. Yeah.
Yeah, it's not an actual thing.
Yeah,
right.
it's kind of
okay.
like lens flare.
Yeah.
This is Louis Gabriel Thibault, and he says, or Thibault. He says, Dr. Tyson, Lord Nice, and Dr. Ivezic, this is Louis Gabriel Thibault. Did you get it right, Chuck? Yeah, I did. How about that, Louis?
Did he say?
He actually said that. Okay.
People rude. People Chuck don't get no
Come
respect.
from me, man. He says from Quebec, Canada, straight north of New York. What was the construction risk that came closest to impacting this project, and what did you do to avoid it? So, were there any risk factors that you almost realized that could have placed the project in jeopardy, or at least delayed it?
And I'm trying to picture this. How do you move an 8-meter mirror into place? What road do you travel that on? Or is it carried vertically? And if it's vertically, what happens if wind comes? Or did you build the mirror on location?
These are all fantastic questions. We had many risks. Fortunately, we either mitigated them or they didn't materialize. We carried mirror in horizontal position. There is a tunnel when you go up the summit where the observatory is, from La Serena in Chile. You take a road for an hour, public road, then you go to AURA compound. AURA is Association of Universities for Research in Astronomy, which is an association of about 50 universities and other institutions.
And it's funded by the National Science Foundation.
Yes,
Yes,
and NASA too. So
And
it's
NASA.
a federal funding from US. And the tunnel is just a couple of inches wider than the mirror.
Ooh,
So it took hours to
gonna
go
say
through a
that.
few hundred yards.
to inch through the tunnel.
Man, I would hate to be the dude driving that truck. I do not want that
Hey,
job.
where's the top part? Where's the top half of the mirror? Well, we left it at the.
Oh my gosh.
Wow.
That poor person, whoever they were, they had to be dying.
What would you
before-
have done if it was not wide enough?
Probably hire a helicopter and just take it up there, but it's much riskier operation, much more
Right.
expensive
Much more
operation.
expensive.
Plus, helicopters are less good at high elevation.
Yes.
'Cause they need
don't-
lift.
They don't have as much stuff to
Air.
push against.
Right. You need like turbo
Yeah, you need
helicopters
some-
and things.
Right. Oh man.
Oh, cool.
Oh man, I'm still feeling bad for that driver. Just waiting to hear the sound. And just like, oh,
Plus, nowadays mirrors are pretty thin, right? What's the thickness of this mirror?
Depends what you count, but if you look at the support too, then it's maybe 1.5 feet, something.
Oh,
like
even that thick. Okay, so it's not a flexible mirror. You're not.
It is flexible, but it's got a honeycomb structure. And then we have 150, I think, 6 pistons underneath.
That's what I was wondering.
That's called the active optic system that deform the mirror. The mirror gets deformed by gravity as you point to different parts of the sky. And then these pistons, again, make a perfect figure to get the sharpest possible image.
Wow, that is really...
And it does it like 10 times per second. It's like crazy. You look at the image, you calculate where you need to push it, pull it, and you do it 10 times per second.
So this fixes the gravitational distortion of the glass, but do you also have adaptive optics?
We don't, because you can't have such a large field of view and adaptive optics. You can make adaptive optics work over maybe a few centimeters field of view, but not like 2 feet across.
Okay, so the Keck telescope will still have value to an observation you might make. With its adaptive optics, it might be able to see more detail than
Absolutely,
you can.
Absolutely. They could be great follow-up instruments.
Great follow-up. Good. Okay.
Wow.
All right, what else you got?
Great
Chuck?
question.
Time
This
for a couple
is,
more.
Stephen Schultz, who says, hello from the birthplace of aviation. Stephen Schultz here.
Wait, birthplace of aviation?
That would have to be Kitty Hawk.
Yeah, I guess so.
Yeah.
Or North Carolina.
Or
North Carolina.
Yeah. Does he say?
No, he says, first off...
We just have to know.
Yeah. He knew what he was doing when he did that. First off, thank you, Dr. Tyson, for diligently working to spark people's curiosities for the cosmos. What all needs to go into consideration when deciding where to build a telescope
that.
of this magnitude?
I love
so
that.
why that location?
Why Chile? Right. So first you want to go to a place like Chile. You want to go high.
The Andes Mountains goes the complete length of Chile.
Right.
So he'd say go to Chile, you got mountains galore.
That particular location, like that peak, was part of that aura property that is already developed. There is a road. Then there is SOAR telescope. And then
SOAR, S-O-A-R.
SOAR.
Yes, that's
I
an
forget
acronym.
what
Yeah,
it stands
okay.
for. And then there is CTIO, which stands for Cerro Tololo Inter-American Observatory, which is half an hour away from our site.
That's where I got all my thesis data was from CTIO.
Oh,
I've
very
been going
nice.
to Chile, multiple
So
times
there
a
is
year.
this aura-supported infrastructure, including roads and other observatories that provide infrastructure.
But so that kept the cost down. You didn't have to build
Yes,
a road
exactly.
and level out a new mountaintop. And because other telescopes are active there, there's good statistics on
Absolutely.
what observing conditions you can expect.
We
Right.
knew it was a very dark site. It's
Yes.
important that there are no lights polluting your background.
Right.
And we knew that we had many clear nights per year, and the atmosphere was very stable, so our images are very sharp. Like if you wanted to go, say, to Kitt Peak, Arizona, that is also a storied place to observe, it's not as good in terms of darkness because they are nearby big cities. It's not as
Tucson,
good.
Arizona, I think, is right nearby.
And then it's not as good in terms of atmospheric stability. We get better image quality in Chile.
Is that because you're off the ocean and there's a
It's
certain
combination,
layers?
geography, ocean and Andes together.
Yeah.
Oh, wow. Yeah, you're like shielded on one side, and then the ocean, I mean...
Well, this is stability. I mean, this is why Hawaii does so well, right? There's
Exactly, very similar.
Yeah.
effect.
Yeah.
So at laminar flow, I think, instead of turbulent flow.
Right.
Well,
Canary Islands too. That
I forgot about them. Yes, of course.
Oh, very cool.
All right.
Well, that was a good question. Thanks, Stephen Schultz.
Chuck, I think we have time for one more.
All righty. How about Chris Ayala, who says, dearest Dr. Tyson, Lord Nice, and Dr. Ivezic, Chris Ayala from New Jersey here. And my question is, what are your greatest fears and aspirations for this project going forward? Ooh,
That is a great question.
yeah.
Let's start with fears so we end up on good note with aspirations.
Okay,
good.
There you go.
And by the way, if something breaks next year, is it your fault?
Next year, it will be fault of my colleague called Bob Blum. He will be new director.
Whoever's the director at the time.
Like the French king said, flood after me or something like that.
Okay, all right.
So let's hope that doesn't happen. But yes, if we broke mirror, you cannot just go to a grocery store, get new one. You have to wait for years.
You can't even go to Home Depot to
You
get
can't go Home Depot. It's something that is not optional.
What would break the mirror?
Something falls onto it. Maybe we try to maintain something and we are not careful. And there are not many examples in astronomy where people broke mirror, and especially not large mirrors. There are very complicated procedures where every step is prescribed like ballet. You just don't go there and do what you want.
It's already pre-established. But
Yes.
sometimes there's a risk that you don't know was a risk. That's how they decide when they put in a traffic light on a country road. You do it after there's been accidents.
Exactly.
Because the stop sign
then
didn't work.
camera is the largest camera in the world, very complex, and there are things that can go wrong with it.
Right.
Maybe it's vacuum, it's cooling, and things like this. You cannot guarantee that.
Oh, that's right. You cool the chip.
We have to cool the chip to like minus 100 centigrade.
Otherwise, it would detect itself.
Yeah, it would look like, people from your generation, you remember those old TVs when there was snow on TV?
Yeah.
That's how
Static.
our images would look like.
Yeah, it would just be all noise if you didn't cool it down.
Right.
Okay, so and that would be fundamental to the flow of the data stream. If that, okay.
Then there is also possibility that we don't get funding to operate it, but I'm not going there. I'm going to switch to aspirations.
Yes, okay.
So aspirations are that we fulfill everything we promised, all the science projects from cosmology to hazardous asteroids, that we deliver on what we've been saying for 2 decades we will deliver. Then next, that we will have some unknown, exciting result that will be perhaps even more exciting than everything else that we planned for. That would be like a great super thing to have.
And let me insert there, is there a serendipity mode, either in the software or in the targeting, where kind of like when Hubble, the director of the Hubble Institute said, let's point it to a random place.
Darts that nothing may
where
be
there's
there.
nothing there, just see what happens. See what happens.
We talked about it, we just didn't call it that. It's target of opportunity observations for LIGO, for neutrinos, those 2%. That's when we interrupt what we are doing.
Got you. Okay.
And we do something different. But because we scan the sky every few nights over and over and over, serendipity will come by itself because you basically look at everything on the sky.
Of course.
Right. Wow.
That's he said it. Because any typical telescope, you have an observing plan because you already know what you want to look at.
Right.
Because I already predetermined this is interesting. That means I'm not looking at this thing. I don't know if it's interesting, but I know this is interesting. Right. And this goes undetected, unexplored.
But when you're looking at everything, you don't have that problem.
You don't have that problem.
That's pretty cool. That's really cool.
Oh, yeah.
Well, this is an opportunity to say for all of our listeners, this is where you have to call your senator and tell them, do not defund science. Do not take money away from science. You're not giving us any money in the first place. So it's not like there's a lot to take away. So just leave it alone so that we can continue doing these type of projects that actually are for the benefit of all mankind and the entire globe and our future as a species. So yeah, keep your grubby little hands off of our science money. There you have it.
Lord nice. I love you.
Suppose you don't like money getting spent on art or on science. These are frivolous activities done by people who are on the fringes of society. And I suppose you could do that. You can create a country that allocates no money to the creativity expressed in art, the creativity expressed in science, or other exploits of human curiosity. You could do that. But think about it. Is that a country you would want to live in? A country with no art, no science, no discovery of any kind, no cosmic discovery? Holding aside that we might discover an asteroid that would render us extinct, seems to me we'd want to know about that. Seems to me. But how about the rest of the splendor and the glory of the universe brought to us by frontier telescopes? Not only on Earth, but in space. This is an activity as old as what it has been to be human, to look up and wonder, what is our place in this universe? I don't know anyone who has not looked up and thought that or felt it. Nobody looks down and has those thoughts. It's by looking up. I'm imagining if you're in Congress and they say, why should we fund science? Well, what value does it play in national defense? Or the art projects that you have in mind, or anything else that's just a pure expression of human curiosity in this world. My only answer would be, Senator, it creates a country worth defending. And that is a cosmic perspective. Well, thank you for being on StarTalk.
Thank you again for inviting Rubin.
Oh, that's your new name now, Rubin.
It's my team. It's
No,
our
that's
team.
that's a great. It's like you don't talk to me. You're talking to the whole team and everybody who
Whole team,
in a
400
collective
people.
effort. Yeah,
It's the
Okay.
greatest astronomical discovery machine ever built.
and nobody can say anything.
Greatest movie of all time.
No, you just went
And I'm
Tom.
not
You just went Tom Brady on us. Yeah, I mean,
It's a fun fact.
Yeah, some people call me the greatest of all time, but I mean, like, I don't have to. I just let other people do that.
Rubin is Michael Jordan of astronomy.
There you go.
Thank you, guys.
Yeah, so Dr. Ivezic, thank you for flying all the way here to New York for this from UW,
Pleasure
Seattle,
was mine.
Washington.
Thank you.
All right. Chuck, always good to have you, man.
Always a pleasure.
All right. As always, I bid you to keep looking up.